Hi there, welcome back to the formulaic approach. Now in this video we are going to be covering electrochemistry. I promise you by the grace of God that if you stick with me till the end of this video, there is no way you will not be able to cross your exams as far as electrochemistry is concerned. We hope to cover topics from the scratch, including redox reaction, which is very essential for this topic, redox reaction, ionic theory, then electrochemical cells, including Voltaic and Galvanic cells and electrolysis. Now, if those two have been your problem, don't worry. By the end of this video, there is no way you will not get it. By the grace of God, I promise you that. I promise you that. So make sure you stick with me till the end. Then, of course, do want to subscribe to the channel if you have not already, please, because it helps the channel. Now, let's get into it already. So now, what is electrochemistry? So as a layman from a distance, you can just say that when you see the word electrochemistry, it is dealing with electricity and chemistry. Maybe even chemical comes to your mind. So you are not still in the dark. You're not still in the wrong, rather, to think that is having to do with electrical energy and chemical energy transformations. Is that okay? So basically, primarily we'll say that electrochemistry is the study of how electricity is made and used up, okay? So that's primarily what we want to study, okay? So we're going to be studying systems that transform electrical energy, into chemical energy that can do useful work. Is that clear? And of course, systems that can do otherwise. So there are systems that will convert electrical energy to chemical, and there are systems that will convert chemical back to electrical. Is that clear? So those are systems that we want to see. Okay. So since they are not in equilibrium, let's use this full. So there's a conversion from electrical to chemical, and then from chemical to electrical. That is what we want to see primarily, okay? But before we see this, there is a very important process that occurs, which is redox reaction that we must understand, and in order to understand how the transformations take place. So primarily, we need to understand redox reaction. Now, redox reaction, I've already covered this before in my previous videos, so I will link it in the description. But again, if you have not studied it, the goal of this video is to help you go from the scratch to finish as regarding electrochemistry. Do you understand? So we're going to still deal with it, all right? Now let's go. What is redox? Redox is basically an amalgamation of two words. We have reduction and oxidation reaction. Reduction and oxidation. Okay, so now actually these two terms are defined chronologically based on their chronology of development of how the definition developed over time. That's what I'm trying to say. So, but I will not give you all the definition. I will not give you the definitions that are of consequence to this video. So we have, for example, we start with oxidation. The first one that you need to know is actually that oxidation is defined as the gain of electrons. So the gain of oxygen, the gain or addition of oxygen to something, of oxygen. Here I'll use O for oxygen, is that clear? So that's oxygen. Then reduction will be the opposite. So that's the first thing you should know. They are equal and opposite to each other. Now what happens is that in any chemical reaction, in chemical reactions, reduction and oxidation always happen. Okay, so when you see one side of a reaction, a reduction happening there, then the other side is oxidation. I mean, like, if you're going to see how we pick it here. Okay, so from here to here is reduction, then from here to the other side is going to be reduction. They always take place, they are reverse processes of each other, okay, and they always take place concurrently. Is that okay? They take place simultaneously in a reaction. So if something is oxidized, the other thing is reduced. That's just the way it is. So reduction is going to be the opposite. If there is a gain of oxygen, the oxygen or addition of oxygen, the oxygen was taken from someone. So that means that that person has been reduced. So it is the removal of oxygen. The removal or loss of oxygen is going to be what? Reduction. So a typical example that I'll give is, maybe we should react, for example, sodium sodium metal plus zinc oxide, for example, to give sodium oxide plus zinc metal. So we'll put 2 here. All right, so it's balanced. Now, so from here to here, so something happened from this normal sodium metal, right? So it underwent a kind of transformation from here to this place, right? This zinc also underwent a kind of transformation from here to this place. Now I want to know what kind of transformation that is. Look at it. Here, sodium was without oxygen. By the time it got here, it had oxygen. So that is addition of oxygen to it, right? So we call this oxidation. Now, keep in mind that this that we wrote here is the full reaction. So if I pick just here to here, it will be called half reaction. Okay? In the case of cell, we'll call it half cells or half cell reaction. Whichever we want to call it, is that okay? Half cell reaction, half cell, they are both correct. So in this case, this is half reaction, or we call it, since the name is oxidation, so the full name will be oxidation half reaction. Is that clear? Then this one is going to be, of course, the opposite, which is what? Reduction. So this will be reduction half reaction, if we were to write zinc oxide to zinc. All right? Now, so sodium became sodium oxide, that is oxidation. Zinc oxide became zinc, that is reduction, because here oxygen was removed. You see, it no longer has oxygen here. All right, I hope you have gotten that. Now, there is now what we call the agency. All right, now this guy, now the questions may now come out on reducing agent and oxidizing agent. Now listen, keep in mind that you must never go to this product side to pick your answer. And if you are given this question and you are asked which one is the oxidizing agent or which one is the reducing agent, and the option contains this or this, those two options will be wrong. Any two options that contains this and this will be wrong. Why? Because you never pick those agents from the product side. Agents are always picked from the reactant side because they are the ones doing the work. This one is just the product, or these ones are just the product. So these are the ones doing the work. So they are the agents. So is either one is the reducing agent and the other will be the oxidizing agent. Is that clear? All right. Now keep in mind that the reducing agent is the one that is oxidized, and the oxidizing agent is the one that is reduced. Now what do I mean by that? The oxidizing agent is the one that is reduced, right? So who is reduced here? Zinc oxide is reduced to zinc, right? The one that reduction happens to is the guy that is reduced, right? And it will be the oxidizing agent. What does that mean? What that means verbally is just that the zinc oxide is the one that is reduced because it's the one that helps us to oxidize the other guy. So we call it the oxidizing agent, OA for short. Then this guy that is being oxidized is the reducing agent because he was the one that helped us to reduce zinc. He helped us to reduce zinc by abstracting oxygen from it. Okay, I mean, this is actually a displacement reaction. So it abstracted oxygen from it. Then zinc gave oxygen to sodium, so it will be the oxidizing agent. Is it clear? All right. Now, so this is the first definition that you need to know. The second definition you need to know. Now, the next definition here should be the one that has to do with hydrogen, but I will not be covering that. I've told you before that oxidation is also addition of the addition of electronegative elements. I mean, with time they soon knew that since oxidation is addition of oxygen and oxygen is an electronegative element, so addition of an electronegative element is therefore oxidation, and removal of an electronegative element is going to be what? Reduction. So addition of hydrogen is also reduction. Addition of hydrogen is reduction. Addition of oxygen, oxidation. Removal of oxygen, reduction. Then addition of hydrogen is reduction, while removal of hydrogen is oxidation. So soon they knew that removal of an electropositive element is oxidation, while addition of electropositive element is reduction. So, but those four definitions are not of consequence here. So I'm going to go to the next one, which is very important. So now, oxidation is also seen as the increase in oxidation number, ON for short. Increase in oxidation number of an element. When the oxidation number of an element increases, that substance is said to have been oxidized. While reduction will be defined as the decrease in oxidation number of an atom. When an atom has a decrease in its oxidation number, then it is said to have increased. When to have been reduced, when it has an increase in its oxidation number, it is said to have been oxidized. I'm going to show you how to get that in a jiffy. You just stick with me. Then the last definition that you need to know is no, I could even show you a simple equation here. For example, look at Na here plus zinc here, 2 plus. Then to give Na plus, or 2Na plus zinc plus zinc. So, if I wanted to balance this, I'll put 2 here. Now watch, look at this ionic reaction. So zinc here, sodium here. What's the oxidation number of sodium here? Once it is a neutral metal, once it is a metal that is alone, you are not seeing any charge on top. It means the charge is 0. This guy is in its ground state. So the total charge here is 0. Here, what will be the total charge here? It will be plus 2. This charge you are seeing here. Then what will be the total charge here? This is plus 1. But there are 2 sodium ions. So 2 times 1. That will be what? Plus 2. Alright. So now, what do you see here? Sodium went from 0 oxidation number to plus 2. So what is that? Increase in its oxidation number. So that's oxidation. You see it does not negate this, right? You see that? Oxidation. So then from here to here is reduction because it went from plus 2 to what? 0. Yes, and so that's reduction. How did I get 0? There's no charge here. So it's also in the ground state. Alright. Then the third definition that I would give you is that oxidation is also defined as the loss of electron, while reduction, the opposite, will be what? The gain of electrons. Now, there is a mnemonic I give my students to remember this. So for this, just remember Leo, the lion. Now, how does a lion roar? It does like grrr, that kind of thing. I can actually roar like a lion, but I don't want you to click out of this video because of fear. Do you understand? So, reduction is actually grrr. Okay, that's roaring. So that is going to be this. Grrr. Leo the lion roars. Grrr. So, LEO there stands for, Leo, that is Panthera leo, the zoological name of lion. That is loss of electron, oxidation. Gain of electron, reduction. Is that clear? You like that, yeah? I know you like it. Now, let us now deal with how to find oxidation number, because this one is where students have problem. One of where students have problem. So I'm going to find the oxidation number of maybe calcium, of carbon in CaCO3, or no. Let me do for this guy. So PO4, 3 minus, for example. If I ask you to find the oxidation number of phosphorus in this thing, how do you find it? It's very simple. So we don't know the oxidation number of phosphorus in this thing. So, but we know that the total oxidation number here is what gave rise to this charge that you are seeing here. Exactly. If there is no charge there, the total oxidation number, the sum of all oxidation number there will be 0. But here, the sum of all oxidation number here will give rise to this charge. So X plus X was from the phosphorus we are looking for. Then for how about the oxygen? Oxygen usually contributes minus 2. Is that okay? But here there is 4 oxygens. So that will be 4 times minus 2. Each of them will contribute minus 2, minus 2. Then everything should give us minus 3. The total oxidation number there. Is that clear? Now keep in mind that this is the way we write it, 3 minus, not minus 3. But when we want to calculate, we use minus 3. Because that's what it means. So X therefore minus, this times this, minus 8 equals minus 3. So X will be equal to minus 3 plus 8. So X equals to 8 minus 3, which is what? 5. Exactly. So that's why we call this tetraoxophosphate 5. Exactly. So the oxidation number of phosphorus there is 5. What if I ask you to find the oxidation number of this guy? Of chromium in this guy. Alright, so for example, chromium here is 2. There are 2 chromiums, and we're looking for the oxidation number. So we'll use X, but because 2 of them are given, so it will be 2 into bracket X, exactly, plus oxygen always contributes -2, like I said, but there are 7 oxygen, so times 7 is equal to total charge here is what? -2. That is, if we add up all the oxidation number of all the oxidation number of all the atoms here, we should get -2. That's the meaning of this charge here. So 2 times x, that's 2x, then plus 7 times this is -14 equals -2. So from here we have 2x equals -2 plus 14, and then we have 2x equals 12 here, so that x equals 6. So the oxidation number of chromium is 6. So this is why this is heptaoxochromate 6. Is that okay? Ion. Now, the last one I'll do is that of the compound. Now, give me, what if I ask to find oxidation number of, let's do something nice like aluminum nitrate. Aluminum nitrate might not exist. Or magnesium, I don't know. Magnesium NO3, this does exist. Okay, I wanted to write here NO3 initially. I mean, that's in this is what I was saying, that does not, I don't know if it exists, okay? But this is correct by formula, okay? This is correct. Now, look at this. Let's find the oxidation of nitrogen here, nitrogen. So, of course, I know this is trioxonitrate 5, so I know it's 5, but let's try to calculate for it. Now, magnesium is +2, we know that. Then plus that of nitrate. Now, nitrate is already covered in 2, so let's put 2 outside the bracket of x that we're looking for, plus 3, which is always contributing -2 again, then close the bracket. Everything should give us what? 0. Why is it 0? Because there is no charge here. This is not a radical, it's a compound. Exactly, these are radicals. So we have 2 plus 2 into bracket x, so I open the bracket, right? Plus, oh no, let's not open the bracket here. X minus 6 here equals 0. So from here we can open bracket 2 plus 2 into bracket, these are 2x. Don't come and add this, okay? Open the bracket first. Then minus this times this, -12 equals 0. So then you can take this guy here, take that guy there. So 2x becomes 12 goes there to become -12 plus 12. More like add 12 to both sides and subtract 2 from both sides. -2. So 2x equals 10, so that x will be equal to what? 5. You see? So trioxonitrate 5. All right. So we know how to find oxidation number now. So in case you are trying to find oxidation number, this is how to do it. Now let's go to balancing redox reactions now. So how do we balance a redox reaction? Now, how do we balance a redox reaction? Now, when you want to balance a redox reaction, you need the following information first. You can balance in 2 types of media. There are 2 types of media. We have the acidic medium and the basic medium. AB. Is that okay? AB, that's their name. Okay? So now, usually I teach my students to first balance in acidic, then transform it to basic. It's easy to balance in acidic medium, then transform it to basic medium. Is that okay? Now, if you want to balance in acidic medium, it's very simple. It's very, very simple. The first thing another information you need to know is that these are the only things you can add to the equation. You cannot add more than these 4 to the equation. You can add a proton to the equation. You can add an hydroxyl ion to the equation. You can add water. I mean, both of them form water, right? To the equation, and you can add electron to the equation. Aside these 4, you cannot introduce anything again. So you cannot introduce oxygen if oxygen is lacking somewhere. And now when I give you the rules for balancing now, the short rule for balancing, you see why that is the case. Exactly. You can only introduce proton, hydroxyl ion, water, and electrons. Now, when you introduce, because electrons are already inside the atoms, right? That's why you can introduce it. Then water is your solvent, where your equation is, your chemical reaction is going on. The water is protic, is a protic solvent, so you have proton. OH is also part of the ions in water. Do you understand? So that's why those are the only things you can add to your equation. Exactly. They're already there. So you cannot add something new. Exactly. So now what are the steps to balancing? The first one is that you have to balance atomically. Now what do I mean by balance atomically? Balance atomically. How do you balance atomically? The first thing is that you should balance all other elements. Balance all other elements all other atoms. Let's use atoms. Atoms except oxygen last. Except oxygen, that is, balance oxygen last. Now, when you now want to balance oxygen, actually, balance oxygen with water. Balance oxygen with water. Balance oxygen with water. Now, what if you now want to balance? Now, when you balance oxygen with water on one side, so for example, let's say there's a reaction that is here on this right side. Let me give you an example. So, for example, if I say you should balance this, let me see if the rules will contain this place. So, if I say you should balance this redox, for example, so this guy usually turns to Cr3 plus. Now, this space I left here is intentional. I usually leave space here and here. Or you can also write here at the back, because I'm going to include some stuffs. Now, look at this reaction. This is a half reaction, okay? This is a half cell reaction. Now, if I ask you to balance this reaction, you will notice that chromium is here, but there is no oxygen is here, but there is no oxygen here. So if I want to balance oxygen here, what will I use to balance? I will use water to balance it, right? If I use water to balance it, I would have introduced hydrogen, a new species. So I'll now come back here to balance the hydrogen with protons. Is that clear? Because it's an acidic medium that I want to balance in first. Always remember to balance an acidic medium first. So I'll come and balance with protons on this side. So then balance with protons. Now the amount of oxygen that you use to, I didn't add that. The amount of water that you use to balance is the same amount of oxygen that you have here. What that means is this. Here, I have 7 oxygen here, right? Not this number, this charge, okay? This 7 that I have here is the number of water we add there. So if I have 7 oxygen here, I will add 7 water there. That will be 7H2O. Is that clear? If I have 7H2O there, how many protons will be there? That will be 14, because 7 times 2 is 14. So I'll now come back here and add 7 protons. So the way we put the statement is that balance oxygen with as much oxygen, balance oxygen with water. So the amount of water should be as much balance oxygen with as much number of oxygen. Just remember, balance oxygen with water. The way we put it is that you should use the same amount of oxygen that is on one side. Use the same amount of water as there is oxygen on the other side to balance. Let me repeat that. I'm saying that you should balance oxygen on the other side with as much oxygen as there are on the, so if there is balance oxygen with as much water, balance oxygen with water. Okay, yes, balance oxygen with as much water as there are oxygen on the other side of the equation. Balance oxygen with as much water as there are oxygen. That is, with as much oxygen that we have, that's the number of water we should add. Exactly, that's the language, but you see it's confusing, that's why I didn't use it. So just know that you should balance oxygen with water. Alright, the moment you now balance oxygen with water, then balance water with protons. The moment you balance with proton, usually it is now atomically balanced. Then the next step is to balance ionically. Balance ionically. So how do you balance ionically? To balance ionically is just the charges you are targeting. Just balance the charges. Now, always use electrons to balance charge. Use electrons to balance charge. Now, how do you balance the charge? Add electrons. Simply add electrons. Add electrons to balance positive charge. Okay? Add electrons to balance positive charge. Keep in mind that these electrons always reduce the oxidation, the charge, always reduces the charge. So what does that mean? That when the part you add electron to is the side that has the highest positive charge. So if I have the total charge there is plus 4, and the total charge there is plus 1, where will I add electrons to? I will add electron to this side. Because if this one is total charge is plus 4, and here's plus 1. How many electrons will I add here? I will add 3 electrons. So when I add 3 electrons here, plus 3, because this is minus 3, minus times 3 is minus. So plus 4 minus 3, plus 3 minus 4, plus 4 minus 3, that's plus 1. So they are now equal. Is it clear? So that's the way we balance charges. Now, the moment you do that, the last step, the other steps that you are now to do are to, if you are giving a full reaction, you are now to, equate the electrons on both sides, on both or in both half reactions. Okay? Then, after equating the electrons in both half reactions, that's if you are dealing with a full reaction. But for this half reaction, this is the half cell reaction, and this is where we'll stop. And it's very simple. You just stick with me. After equating them, you now cancel out species that appear equal. Cancel out species that appear on both sides. On both sides of the overall reaction. Okay? So this is primarily it. But what if you now want to add, what if you now want to balance in basic medium? If you want to balance in basic medium, so I'll say in basic medium, just try to squeeze, I want to squeeze this in. So this is the end for balancing acidic medium, okay? There's just one step for balancing in basic medium. In basic medium, so I'll just put BM for basic medium. In basic medium, add as much OH minus as there are H plus, and this is what I wanted to make in that expression before. As there are H plus to both sides of the reaction. So you should add as much OH minus as there are H plus to both sides of the reaction. Because the truth is, at the end of the day, when you balance an acidic medium, what represents an acid? Protons. So you now use OH to neutralize the amount of H plus that you have there. So if you have 2H plus in the entire reaction, you add 2OH minus to neutralize it. You now add it to both sides. It has turned to basic medium like that. Is that clear? So let's do that. I will show you how to balance this in acidic and I'll transform it to basic. So let's follow the steps. The first thing is to balance atomically all other atoms except oxygen. How many chromium do we have here? We have 2. How many chromium do we have here? We have 1, right? Not 3. 3 is the charge, okay? So we have 1 here, or 1 mole here. So we come and add 2. Never come to add this molecule, number of molecule here. Come and add mole here. Exactly. I've told you that in balancing chemical equation. So when you do that, chromium is now balanced. How about oxygen? We are balancing it last. Balance oxygen with water. So how many water do we have? How many oxygen do we have here? We have 7 oxygen. We come here that there is no oxygen at all. We add 7 water. So by adding 7 water, you have added 7 oxygen. Is that clear? But of course, by adding 7 water, you have also introduced a new species, which is proton. So you come and add equal amount of protons as there are hydrogen on this side. So how many hydrogen do I have on this side? 14 hydrogens. So I'll come and add 14 protons. 14H plus. Is that clear? This is not hard. I've balanced oxygen with water. I now come back here to balance hydrogen, and that's the way you'll be going. Is that clear? Then the next one is now, so I'll now balance ionically. The moment you balance the protons, usually they are balanced atomically. CrO is 2, O is 7, O is 7, H is 14, H is 14, balanced. How about the charge? Total charge here is 1 times minus 2, that's minus 2, because it's 1 chromium and 1 chromate ion plus here 14 charge. This one is plus 1 times 14, that's plus 14. Here's minus 2 times 1, minus 2. So 14 minus 2 is what? 12. Plus 12 is the total charge here. How about on this side? Total charge on this guy, since there is no charge here, is 0. Plus total charge on this guy is plus 3. But there's 2 here. So 3 times 2 is what? 6. So total charge on this side is what? Plus 6. Now, where do we have the highest charge, the highest positive? This side. So where are we adding electrons to? This side. Add electron to the side that has the highest positive charge. So how many electrons are we going to add to this 12? to give us 6. So we just need what? 6 electrons. So we'll come here and add 6 electrons. Because by adding 6 electrons, this thing would have reduced to 6 minus 6. 12 minus 6 is what? 6. Is that clear? So that's the way it is. All right. So now, the balance reaction is this. Choose the balance reaction. You see the way I balanced in one step? Very simple. Very simple. But actually, this is a half cell reaction. This is a half cell reaction. So that's why I can balance in one step. And electron is still appearing. Once the electron is still appearing, you know it's a half cell, it's not a full cell. For a full cell or complete cell reaction, or for a complete cell reaction, you must eliminate the electrons, because the electrons will appear on both sides for both half reactions. Now, listen to me. Listen to me. Here's one thing you must notice. Remember that the reaction started with just Cr2O7 and Cr3 plus. If I had asked you to find me the oxidation number there, no, let me write it. If I had asked you to tell me, predict whether it is oxidation or reduction, how would you predict? Is this an oxidation of reaction or a reduction of reaction? Now, see what we have here. See what we have here. Cr2. We found it here, the oxidation number of Cr2. We found it here to be 6. From 6, it's turned to plus 3. What is that? That is reduction. That is what? Reduction. Because oxidation number what? Being reduced. If you don't still believe me, let's use another definition. This one says addition of oxygen is oxidation. Removal of oxygen is reduction. And I told you now that this one is reduction, right? This is reduction half reaction. Let's prove it with that definition. Now, what happened to chromate here? It lost oxygen, right? So oxygen was removed from it, right? So that's also reduction. You see that those two definitions prove it now. How about here? Which one proves it? That reduction is gain of electron. Let's see. Was electron gained here? Yes. Electron was gained here. The electron was gained here. If electron was lost, you will see the electron on that side. Is that clear? So whenever you see electrons, that's how to remember it now. Whenever you see electron on your left side, that is reduction. If you see electron on your right side, that is oxidation. Electron on your left side, reduction. Electron on your right side, oxidation. Don't forget. All right, let me balance one more half cell. Then before I balance a full cell, I'll give you a full cell reaction now. So for example, what if we are told to balance something like this guy? Let's use something like SO2 to give us SO4 2 minus. So what if we have something like this? Now, already from what I've taught you, you should be able to tell me if this is oxidation or reduction. Oh, oxygen is 2 here, there are 2 oxygens here, there are 4 oxygens here. That tells you that is probably oxidation, that more oxygen has been added, right? If you want to use that. What if you want to use electron? You can't see electrons here yet, so you can't use this definition. How about oxidation number? You can actually do that here, but I don't want to go through that step, all right? So let's solve already. I'm going to use the methods of balancing, and we will solve it, and we'll be able to do it, and we'll be able to determine whether we are correct. So we are predicting that this is what? Oxidation half reaction. And we predicted that, or we saw that this was actually reduction half reaction. Now for oxidation half reaction, how do we go? The same step, we balance atomically. 1s here, 1s here. Balanced here. 2 oxygens here, 4 oxygens here is not balanced. So what do? We come to add, how many oxygens do we need more on this side? Where do we need more oxygen? Here. How many more do we need? 2. So that 2 plus 2 will be 4. Is that clear? So we cannot come and add 2 oxygen. It's water we'll add. Is that okay? Balance oxygen with what? Water. So we'll come and add 2 water. And I said balance oxygen with as much water as there are oxygen on that side. So we have 2 more water than here, right? 2 more water than here. So we add 2 more oxygen rather than we have here. So we'll add 2 water here. So that we'll have 4 water, 4 oxygen on this side. But of course, by adding water here, we have added what? A new species. What's the new species here? We have added H plus. Hydrogen. So here, how many hydrogen do we have here? That we have added 4. So come here to come and add 4 H pluses. Is that clear? Don't worry. I forgot to balance this in basic, so I'll show you in basic after balancing this. Is that clear? So I balance with hydrogen. You see that I'm going back and forth very easily. Very, very easy. Sorry. So the next one is now to balance. So we are balanced with protons. So I've told you once you get to that protons, you have usually if you follow that step, you must have balanced properly, atomically properly. Let's go ionically. Total charge here, no charge at all, 0, no charge at all, 0. So total charge on this side is 0. Now what's total charge on this guy is -2 times 1 -2 plus total charge here plus 1 times 4 plus 4. Is it clear? All right. So 4 minus 2 is what? Plus 2. 4 minus 2 is plus 2. So now, where do we add electrons to? Add electrons to the side that is more positive. So which side is more positive? This side. So how many electrons are we adding to become this, to become 0? We add 2 plus 2 electrons. Is that clear? The moment we add 2 electrons here, it will be plus 2 minus 2 now, minus times plus. Minus times plus 2. That is what? Minus 2. So minus 2 minus 2 is what? 0. So they are now equal. So this is now balanced both atomically and ionically. Now listen to me. Is this oxidation reaction or reduction of reaction? Now, equates electron both. Now, there's something I wanted to say. Okay, I want to balance. So this is now balance. Sorry, I wanted to now balance in basic medium. To balance in basic medium is very easy. Let's balance this guy in basic medium. Remember, you have to add the amount of H pluses you have in your acidic medium. Add it to your basic medium, right? So, now so that will not be crossing. Let's do this first. Let's balance this in basic medium. Then we'll now balance this one. Or balance this one in acidic, in basic later. So let's balance this one in basic, How many H pluses do we have? Okay, now, the proof of our prediction. When you have electron on the right side, that is what? Oxidation, I told you, right? So that is a loss of electron. Electron was lost here. Remember, electron was gained here. Is it clear? So that's why this one is reduction of reaction. All right, let's go now. So let's balance this in basic. We'll add how much H plus we have. We'll add the number of OH. How many H plus do we have in this reaction? 4. So come and add to this side. We'll add how many OH minus rather? 4H plus. We'll come and add 4OH minus first here. We'll add it to this side too, plus 4OH minus. Is it clear? We add 4OH minus to this side, 4OH minus. If I have 15 here, I will add 15OH minus, 15OH minus. Is it clear? So with that, this one would have turned to water. This side here, and this one we add together to give us water. Remember, water ionizes like this. So this thing means 1H plus 1 OH minus will give us 1 water. So 4H plus 4H minus will give us 4 water. So here we have 4OH minus plus SO2 plus 2H2O. Remember, this one cannot come back and add to this. So give SO42 minus plus this 4 water, right? 4H2O then plus 2 electrons. Is that clear? So now what will now happen is this will now cancel species that appear on both sides. Water is appearing here and here. So let's cancel 2 out of this one. Minus 2H2O, that's 0. Then here minus 2H2O. What will remain? It remains 2H2O again. So our answer becomes 4OH minus plus SO2 to give SO42 minus plus 2H2O plus 2 electrons. Exactly. So see, this is the balanced basic medium. Now what we wanted to do the basic medium for this guy. Basic medium. We'll take the same process. So after this, I'll balance only one more, which will be a full cell. I'll balance one full cell or one complete cell, whatever. A complete cell reaction, and that will be it for balancing redox. Then we'll start our cells. Now, our electrochemical cells. Now, to balance this, I'll just add how many OH will I add here? What's total OH on this side, in this reaction? 14H plus. So we'll add what? 14OH minus. So come here and add 1408 minus, and here come and add 1408 minus. If there was space here, I would have written it here, but there's no space. So if I add 1408 minus here, 1408 plus 1408 will give us 14820. Is that clear? Plus Cr272 minus, keeping in mind that this has gone, has become water, plus 6 electrons to give 2Cr3 plus 7820 plus 1408 minus. Now, this is our reaction. Now there's H2 is appearing here, H2 is appearing here. We'll cancel 7 here and cancel 7 out of this one. It remains 7H2O. So our final reaction becomes 7H2O plus this to give this. Is that clear? And that is the final answer. Now let me clean this side and give you one more reaction. Let's do this reaction. MnO4. Let's see. Let me clean it first. All right. So let's go on to balancing. Let's balance this reaction. MnO4, I think is minus because we have KMnO4. Is minus, not 2 minus. This one becomes Mn2 plus, and this one becomes Cr2. So let's say you are given this kind of reaction. How do you balance it? Now, how do you balance this redox? So we'll pick Mn became this, and this one became this. So those are our half reactions, right? So we have separated into half reactions. Which one will be oxidation? You can already tell that this one from here to here is reduction. So reduction half reaction is MnO4 minus becoming Mn2 plus. Then the oxidation half reaction will become what? C2O42 minus becoming CO2. Now, if this is the case, then we have that Mn, right? So let's balance. Mn is 1, Mn is 1. Balance, not the charge. We are not touching the charge yet. How many oxygen do we have here? 4. How many water are we going to add here? 4 water, equal amount. 4 water. By adding 4 water here, we already introduced 8 protons. So come and balance the 8 protons here. 8 plus. That is already balanced. You see how speedily I went down. The next thing is to now balance the charge. Total charge here is minus 1. Total charge here is plus 8. Total charge here is plus 2. Total charge here is 0. So plus 2 is the final total charge on this side. Total charge on this side becomes plus 7. So now we have 7 positive, 2 positive. So come and add electrons to this side to reduce it. So we add 5E minus that will add, so that when we add 5 electrons to the minus 5, it becomes 2. Is that clear? So our reaction is now balanced like this. Our half reaction becomes MnO4 minus plus 8H plus 8H plus 5E minus to give Mn2 plus 4H2O. So now let's balance this one. C is 2, C is 1 here. We come and add 2 here. So that C is now balanced. Oxygen is now 4 here, 4 here. Oxygen is balanced. So we don't need to add water anywhere. So here, but we'll add electrons because here is minus 2, total charge, here is 0. So where do we add electrons to? 0 is more positive than this thing. Like 0 is closer to positive than minus 2. So we'll come and add electrons there. How many do we add? We add 2 electrons. Is that clear? So when we add 2 electrons, what will happen? When we add 2 electrons here, this becomes balanced, right? So by charge, this becomes minus 2, minus 2. So by charge or ionically, they are balanced. So if that's the case, then we now add up the overall reactions, write the overall reaction. Now, before we write the overall reaction, one thing we must first do is to equate the electrons. Equate the electrons in both sides. Exactly. Now, you know we have balanced electrons now. So you equate the electrons on both sides. How many electrons do we have here? We have 2 electrons. How many electrons do we have here? We have 5. So one thing you must do is, electrons must not appear in our overall reaction. So we'll try and equate this electron by multiplying with a particular integer. Now, how do you know the integer you use to multiply? It's very easy. You have 2 electrons here. You have 5 electrons here. The LCM of 2 and 5 is 10. So how do you get to 10? You multiply this guy by 5, you multiply this guy by 2. Everybody here by 2, everybody here by 5. So someone is asking, what if I have 2 here and I have like 4 here? Very easy. LCM of 4 and 2 is what? 4. So all you need to do is get 2 to become 4. So what you do is multiply this one here by 2. If there were 2 electrons here and 4 electrons here. What if I have, maybe I have 4 here and 6 here, for example, 6 electrons here. Now, 4 electrons here, 6 electrons here. Just take the LCM again. LCM of 4 and 6 is 12. Multiply this 4, this 6. Together, how do you get to 12 from 6? Multiply that 6, that expression by 2, so that 6 will become 12, and multiply this one by 3, this one will become 12. Is that clear? So that's how to do it. So the next thing you do is multiply like that, and our reactions become, here this side becomes 2MnO4 minus plus 2 times this, 16H plus 10E minus to give 2Mn2 plus 8H2. Now the mistake students make is to not multiply everybody by that number, that integer. That is a mistake. So make sure that you don't commit that error too. 5 by this guy becomes 5C2O42 minus to give 10CO2 plus 10E minus. Now, given this, we now bring the overall reactions together. Now, this way you bring the overall reactions together. This is reactant side, this is reactant side. You bring them together. Reactant side together. So, the way to write it is to write the major guys first, okay? But anyway, you can write it like that. But I like to teach my students, write this first, before this, then before you now write all this one. These ones are subsidiary, so you write them last. But if you don't understand, just write everything. 16H plus 10E minus. But make sure you see my video on balancing redox separately. I think I did more examples there. Then those are the reactants together, because in the former reaction, these are the reactants, so it was contained here. Yes, sir. These are just the new terms that came in. Then the products, this guy and this guy. So we have 2Mn2 plus 8H2O plus 10CO2 plus 10E minus. I hope this thing is still recording. So by the time we do this, so electron is on this side, we cancel out. Electrons on this side, it cancels out. What else? What else? Nothing else. Nothing else. So our final answer, our final overall reaction becomes 2MnO4 minus plus 16H plus 5, no, let me write this correctly now, 5C2O4 2 minus first plus 16H plus. Is that clear? To give 2Mn2 plus 8 plus 10CO2 plus 8H2O. You write these ones later. Is that clear? Now listen to me. If you check this, it's already balanced, so I don't need to confirm again. So if you check out that video, I'll show you. I showed how to confirm if your expression is correct. Now let's go to our cells. Now you have not been listening since. You have not been listening well since. This is the major part of this lecture, because all these things that we just did, they're the foundation for this part. So make sure you listen, please. That's why I'll take my time on this part very well. So now we want to discuss our cells, the electrochemical cells. The electrochemical cells. Please make sure you listen to this part very well. Very well. Listen very carefully. Now the first cell, okay, so we have electrochemical cell. Now the first there are two types of electrochemical cells. We have the voltaic or galvanic cell, and we have the electrolytic cell. Now, first, I'd like to teach you the voltaic and or galvanic cell. But the first thing I want to do is to first differentiate between them for you. Let me first differentiate between them quickly. It will help you to have a good foundation. Now, for voltaic or galvanic cell, then electrolytic cell. Now, what's the difference between a voltaic and a galvanic cell? The first thing that is very, very important is that for voltaic cell or for galvanic cell, the voltaic cell uses chemical energy, transforms rather chemical energy to electrical. Okay, so there's conversion of electrical energy to make electricity. Conversion of electrical energy to electrical, chemical energy to electrical energy. But for electrolytic is the opposite. This one uses electrical energy to drive a chemical process. Do you understand now? So electrical energy is converted to chemical energy in an electrolytic cell. Another difference is that voltaic cell, the chemical reaction, is a spontaneous process. Is a spontaneous or feasible process. That's another word, feasible process. So, while an electrolytic cell is a non-spontaneous or non-feasible process. Now, you remember in our thermodynamics, I did show you that the change in Gibbs free energy that denotes the spontaneity of reaction is a negative value for Gibbs free energy. So when the Gibbs free energy that is in a chemical reaction is given, the Gibbs free energy for a given chemical reaction gives you a negative value, then that reaction is spontaneous. Then for this guy, the change in Gibbs free energy is actually positive. It's means what? Positive. What if it is zero? It will be an equilibrium reaction. Now, another thing you should know is about the electrodes. Okay, now there's another terminology actually that we use to denote the spontaneity of a reaction or the feasibility of a reaction. Now, that term is called the electrode potential. The electrode potential. Now, you know it as, in physics, you know it as voltage. Voltage can be seen in terms of both potential difference, okay, or electromotive force, EMF. Is that clear? Now, but there are many names we call it. If we are referring to a cell, we call it cell potential. If we are referring to a given electrode, we call it electrode potential. Do you understand now? So basically, all of them are talking about electric potential, which is still voltage. Then, now, so if the value for E cell, I'm going to show you the relationship between them, okay, in an equation now. If the value for E cell, is positive, that's what I wanted to remember. E cell, if your E cell is positive, then your reaction is spontaneous. But if your E cell, for a non-spontaneous reaction or for an electrolytic distance, the E cell is what? Negative. The E cell is negative. Now, what's the relationship between them? It's very simple. You just watch me. Focus. In physics, this E cell will be voltage, so we use V. Is that okay? Recall in physics that voltage is what? Or electric potential is what? The work done per unit of charge taken from infinity to a point. Now, I want you to understand this concept. I'm going to demystify something for you in a while. You just listen and you will understand. I'm going to switch a little to physics now. Just watch. So, this is work done per unit of charge, okay? Now, and you know that work done is energy, right? So I could say energy used up per unit of charge, right? Per unit of charge brought from infinity to a point. So it means that energy here, in which case we'll be referring to Gibbs free energy, is equal to Q times V, right? QV, right? QV. Now remember that this V, I said, is the same as this E cell, right? So I'm saying that energy E is going to be what? E cell. So let's change this energy to Gibbs free energy. gives free energy. So, but we usually use delta gives free energy because it is relative. It's a relative term. We'll take it from, it's usually compared like initial to final. Do you understand? Do you understand? So, it's a state function. So, gives free energy is equal to E. Gives free energy is equal to E. Q times this V is now our E cell. Is that okay? E cell. Are you following? Now remember that Q is quantity of charge, right? Or quantity of electricity, right? So, and remember that the quantity of electricity is talking about how much Faraday is used up. Now you remember that 1 Faraday is equal to 96,500 coulomb of charge. Is that correct? So it means that the quantity of electricity is actually number of Faraday that is used. This is quantity of electricity in coulomb, and this is the number of moles of Faraday. If it is 1 Faraday, it will be 96,500 coulomb. So quantity of electricity is number of Faraday. So change in this free energy is actually equal to, now, there is a caveat to this. We usually add a negative value, and I'll tell you the reason. So that is NF, which is Q times E cell. So that's how the formula is derived. Now here is the case. You see, now this negative, what this negative does is this, because there is, in measuring E cell, there is an orientation, there is a way it is done. So because of that, because of the way it is done, we need to add a negative value here so that when we take the value, by the time if E cell, you to look at this, if E cell is positive here, then that's only when this free energy can still be negative, in which case it will now be spontaneous. You see, they don't negate each other now, they correspond. Now the next case is here. If E cell is negative, so negative times negative, positive, so gives energy to positive for a non-spontaneous reaction. You see, is they are both saying the same thing now. Now let me show you something. Another thing I want to show you, another difference. So I've mentioned 1, 2, 3, 4. Now, how about, so 4. Now the fifth thing I want to tell you is about the electrodes. Electrodes. Now there's a reason why I give you a box here. I want to explain something. Here, let me put E cell. E cell is negative. Now just stick with me. Now the electrodes here, there are two types of electrodes. We have the positive, the anode and the cathode. Now, what confuses students is this. That which one is positive, which one is negative. Now I will show you how to get it without cramming. But for now, I just want to show you the difference. Now, for this case, anode and cathode. Now, in this case, in this cell, the anode is negative in Voltaic cell or Galvanic cell, while the cathode is positive. Is that clear? But in electrolytic cell, anode is positive, while the cathode is negative. I'll tell you why. Let me quickly explain what happens. Let me quickly explain how it is to you. For those of you who already have an idea. Now, for a battery, you remember that conventional current flows from where? From positive to negative. Conventional current flows from what? From positive to negative. The reason is that, now, what is even driving the current? It is voltage, right? Okay. Why does current flow from positive? Conventional current flow from positive to negative. First, know that conventional current is defined in terms of positive charge and not negative charges. Electrons are negative charge carriers. Electrons are the ones that are moving. That's what constitutes in electricity. Because what we want to discuss in Voltaic cell now is how electricity is being produced. So electrons are the ones moving. So when electrons move, how do things naturally move? So if electrons are the ones moving, so it is a spontaneous reaction, right? By themselves, they want to move. How do things want to proceed naturally? Look at this marker here, that is I up here, and this marker that is here. This red marker and this black marker. If this one, they are both writing black though. Now if this one goes, which of these two markers, if this black marker, between this marker and this red marker, which one have is at a high potential, which is at a low potential? Now this one here is at a lower potential than this guy. This guy has a higher potential than this guy. Is that clear? High potential than this guy, low potential than this guy. Or high potential energy, low potential energy. Keep in mind, potential is different from potential energy. Gravitational potential is the potential at this point. Gravitation, and of course, I've switched from gravitation, electric to gravitation, but it's easier to use gravitation. That's why I switched. It's easier to understand gravitation, and you will understand. You just stick with me and listen to me. Here is higher potential, right? So this place has a high potential because this place has high potential energy, and this place is also having high gravitational potential. Remember that the potential energy is, just remember that potential energy is mgh. So it's a function of height. So the higher the height above the ground, the higher the potential energy, right? So this point here is at a high potential. What that means is that the work done in bringing this unit mass, if this was a unit mass, of course this is not a unit mass, if this were a unit mass, the work done in bringing that unit mass from any point of reference, maybe infinity, for example, from the ground, for example, if that's our reference point, to that point, that is the gravitational potential at this point, is a term that is relative to position, that is dependent on position rather than the mass itself. Is that clear? Of course, also dependent on the mass, But I'm saying that is a position function. Do you understand? So that if this guy is higher up here, this point is at a higher potential than the initial position. Is that clear? So this point here has a higher potential energy than this guy. So if I release this guy, where will it naturally go? Will it go up or down? Now it will not continue up, because to go up is a higher energy. It requires a higher energy. But to go down, it takes no energy at all, in fact, because it will be reducing its energy. So every object wants to try and reduce its energy as much as possible. So when I release this guy, it goes down. Do you understand? So going down, it means that it will go from high potential point towards a low potential point. So our electricity too, in a battery, if these are the two terminals of a battery, let's call this terminal, let's call it positive. Let's call this terminal negative. Now, when you say current flow from positive to negative, when you say current flow from positive to negative, we are saying that this point positive here is the one that is at a higher potential than here for a positive charge. Stick with me. This point has a high potential for positive charge than this guy. So for positive charges to be moving, so when we say current is flowing, current we say is flowing, current is the rate of flow of charge, right? Rate of flow of charge. So this charge here, we are referring to positive charges in this context. So positive charges are actually flowing to negative. They're flowing to negative. Immediately you connect a wire like this, the current will flow like this and we enter this side. Why? Because for a positive charge, this point is at a high potential. Things naturally want to move from high potential to low potential. So for a positive charge, this point is a high potential point, and for a positive charge, this point is a low potential point. So it wants to flow from here downward here. But for electrons, this point is a high potential. That's why it is moving here. Why is this point high potential for positive charge and this point is high potential for electrons? Electron is a negative charge carrier. Remember that. So for a positive charge carrier, for example, which is proton, but of course protons do not move, but for a positive charge, this point is high potential. Why? Because remember the law of electrostatics, like charges repel. So if a positive charge is here, it is at a high potential point. Why? Because that point naturally wants to repel, because that point is positive, so a positive charge is going to be repelled away from here. So that's why it takes high energy to bring a positive charge to this point. I will link a video in the description where I've explained something like this before. If you bring a positive charge to this point, it takes high energy. It's hard work. So for the positive charge to be staying here is not very convenient. So what it does is, once you bring a conductor, the guy naturally runs to a point of no distress. Do you understand? Now, why is this point a high potential point for negative charge? Because negative charge, electrons are negative charge carriers, and negative charge repel negative. So if negative charge repel negative, so electrons are naturally being repelled here, but they have to stay here because there is no conductor to bring them out. The moment you put a conductor here, the electrons begin to what? Flow to a point of low potential. So this positive end is a point of low potential for electrons, while this point is a point of high potential for positive, and this point is low potential for positive charge. Is it clear? So that's why positive charges flow from positive to negative, which is the direction of conventional current, while electrons flow from negative to positive. So in a galvanic cell, in a galvanic cell, which we will see now. No, since I've built that foundation now, let's go to galvanic and voltaic cell. So I don't need to write this again. Let's go to the galvanic and voltaic cell. Let me clean this side of the board. Now, listen to me. So for a voltaic and a galvanic cell, the principle of operation of this thing is just how a battery operates, and that's why what I basically want to teach you. Now, basically, why is it called voltaic or galvanic? There are two scientists here. We have Alexander Volta and Ludwig Galvanic, who in the year 1793 actually produced the first battery that he called the pile. That is Alexander Volta. He made the first battery and he called it the pile. Okay, I'm going to make a video on history of electricity, and then I'll tell you how that is. So now my point is that these two guys were proponents of a particular course, and that was why they named this after them. Now for voltaic or galvanic cell, there are some terms that you have to first understand, okay? Now, the first term that you must understand is what we call the electrolyte first. You must understand an electrolyte. What's an electrolyte? An electrolyte is a substance that in molten or solution form can conduct electricity. In molten state or solution can conduct electricity. Molten form means a paste, like a paste, or a solution can conduct electricity. Okay? Now, what happens to an electrolyte? What happens to an electrolyte is that electrolyte is basically first in solution. Remember that a solution is basically a solute plus a solvent, right? Plus a solvent. Now, in this case, our universal solvent is water, so we are going to be talking about water basically. So our solute is the salt that is dissolved in the water. Is that clear? Now, according to ionic theory that was propounded by a certain Swedish scientist, that's Svante Arrhenius. Now this guy in I think 1887 propounded the ionic theory and said that when substances dissolve in water, they dissociate. When substances dissolve in water, or dissolve in a solvent, dissolve in water, for example, they dissolve in a solvent, they dissociate into freely moving charged particles that we call ions, called ion. So now when substances dissolve in water, they form ion. Now those ions are the things we are going to talk about soon. But the degree of their dissociation determines the degree of their conductivity too. So for that reason, we have two types of electrolytes. We have the strong electrolytes and the weak electrolytes. Now the strong electrolytes are the ones that when they dissociate, almost all the particles dissociate, they dissolve in water. They turn to ions, almost all the particles. But weak electrolytes, not all the particles turn to ions. So for example, KH is a strong electrolyte, NaOH is a strong electrolyte, CaCO3 is a strong electrolyte, NaCl strong electrolyte, because most of all of these guys, when they dissolve in water, they dissociate almost totally. But look at something like this guy, CH3COH, ethanoic acid is a weak electrolyte because it only dissociates partially. So substances that undergo partial dissociation, they are what? Weak electrolytes. Now, strong electrolytes dissociate almost completely or completely. Is that okay? And because of that reason, they allow for more conduction of what? Electricity. Okay? So remember, the main goal is that these guys are conductors in molten or solution form. Now, another thing that conducts electricity is also the electrode, and there are two types of electrode. We have the anode and the cathode. The anode and the cathode. Keep in mind, remember that I said this guy is negative. I can't even remember now. But when I explain, you will know whether I'm correct. For a galvanic cell, the anode is the negative electrode. So if it is the negative electrode, now you should remember the definition of anode and cathode is not basically this. It's not this, because it changes for electrolytes. The only consistency is that whether it is negative or positive, it is the electrode. An anode is the electrode where oxidation is the site for oxidation. Anode is the electrode where oxidation occurs, while cathode is the site for reduction. It is the site for reduction. Alright? So here is the site where there will be loss of electron, while here is the site where there will be gain of electron. Is that okay? Now, another thing you should know is we know electrolytes, we know electrode now. The other thing you should know is ionization. Of course, according to ionic theory, that is just formation of ions. Is that okay? Formation of ions, and there are types of ions. So this ionization follows what? Voltaic principle. We call it the ionic theory. Okay? Formation of ions following ionic theory. And I'm sorry I'm kind of rushing now. The reason is I was shooting this video almost 2 hours yesterday, or even more than 2 hours, and everything got deleted because there was no space on my phone. And the space is already running out again. So I'm trying to, well, just stick with me, you understand. So following ionic theory, ionization occurs. Now, when ionization occurs, how does it occur? Let me pick anything here, for example. Now, I'm going to be doing electrolysis of brine, so let me first ionize that guy for you. So for NaCl, for example, how do you ionize it? When it enters water, when it enters into water, what it does is it will dissociate into Na plus and Cl minus. Is that clear? What about, we are going to be dealing with copper sulfate in this our galvanic cell. Copper sulfate, for example, when it dissociates, it becomes Cu2 plus SO4 2 minus. Is that clear? And SO4 2 minus, so the plus is not necessary. How about zinc sulfate, for example, when this guy dissociates, it becomes zinc Zn2 plus SO4 2 minus. Is that clear? So this is how to ionize substances. You must put the charge because ions are charged particles. Is that okay? When an atom becomes charged, it forms an ion. It has become an ion. Now, having known these terms, let's now go to galvanic cell proper. Now, what are the components of a voltaic or a galvanic cell? What are the components? Now, the reason why I left my number there is so that you can reach out to me for questions. If you have questions or you want me to send you questions on calculation, that we will do soon. Now, what are the components of a galvanic cell? Now, it contains a galvanic cell comprised of a container, or two containers basically, two containers. One will be, both of them will be housing electrolytes. They'll be housing electrolytes. So what is an electrolyte? The electrolyte here that you find here is going to be zinc sulfate, okay? And the electrolyte you find there is going to be copper sulfate, and there is no mistake here. Don't come and place copper sulfate here and place zinc sulfate here. There is a reason. I am going to tell you why. Because the idea is that there is a formal way of doing this. Now, how do you put zinc here? You know zinc sulfate is going to be salt, powdery salt, right? What you do is you add water and pour your salt inside and mix it. When you pour your salt inside, what you will find inside that salt, inside this place, is ions. Who's that? What you will find inside this place are the ions of this guy, which is what? Zinc 2 plus, 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 Zn2 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 plus. Now I'm leaving this space for a reason, okay? Zn2 plus. Now you now immerse something inside. That thing is called your electrode. This guy is your electrode. It's a metal, okay? It's going to be a metal. So Zn2 plus, Zn2 plus, Zn2 plus. Now then you tell me, Master, you also said that SO4 2 minus. I just remembered. So there will also be SO4 2 minus. 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 Now, the reason why I did not put SO4 2 minus first in the first case is because SO4 2 minus is not a target here. Is that okay? It's not very, very important here. It's not very, very important. But I'm going to show you what will happen soon. So there is SO4 2 minus and Zn2 plus here. Yes, sir. Yes, sir. Yes. So there's SO4 2 minus. Okay? Right. How about here? Copper sulfate will also feel like this. Now, but what metal is here? Now, when you introduce, the metal you introduce here is zinc metal itself. So what you are primarily doing is that you are immersing a zinc plate in a solution of its salt. Is that okay? Immerse a zinc plate in a solution of its salt. So we have zinc plate will contain neutral zinc metal, right? So that as I'm writing just Zn, Zn. That's neutral zinc. That's what makes up zinc plate, right? Zinc plate will comprise of neutral zinc itself. All right. Then here also we are going to have immerse an electrode here also. Okay? We're going to immerse an electrode here. Which electrode is this? This will be the copper electrode, like you guessed right. Copper metal inside a solution of copper sulfate. Okay? Is a solution of copper salt. So when you do this, something begins to happen. From this start, something begins to happen. I'll tell you what. So here, to what are we going to have? We're going to have Cu2 plus SO4 2 minus, Cu2 plus SO4 2 minus, Cu2 plus SO4 2 minus. But let's not focus on Cu2 pluses now. Cu2 plus, Cu2 plus. Now, why am I focusing on Cu2 plus? Because they are the most important part here. Is that okay? Cu2 plus SO4 2 minus, 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 Cu2 plus SO4 2 minus. Someone is saying, I like play. I don't like play. Do you understand? All right, let's go. So we have equal amount of Cu2 plus SO4 2 minus in both right now. Equal amount of Cu2 plus and SO4 2 minus. Now, the moment you immerse a metal plate in a solution of the salt, something is set up. That what is set up is called a cell potential. A cell potential is what is set up. Now, what is a cell potential? A cell potential is just the movement of ions between the plate and the solution. The movement of what? Not ions, sorry, charges between the plate and the solution. So what will happen is that there is a tendency of the metal to want to give electrons to the solution, and there is a tendency of the solution to want to take electrons or pull electrons from the metal plate. So that thing is called cell potential. But it's not measurable until there's equilibrium has been reached, where there is what? Equal measure of pull on electron, as much as there is also push. These guys are pushing electrons, they want to enter here. The same way these guys are pushing electrons, want to enter the solution. These guys are pulling electrons into them. So once that equilibrium is set up, that is when cell potential is measurable. Okay? So it means that these guys already want to draw electrons out. These guys want to push electrons out. Is that okay? But one thing will not happen. You will not know that this is happening here yet until you connect these two. You connect them to each other. The moment you connect these to each other, something begins to occur, and that is movement of electrons. What will happen is that electrons begin to move from here, move 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 here. Then someone is now thinking, now the master, will you see the electrons strolling and say, hey bro, how are you doing? No, you won't see them move. How do we now know that electrons are moving? All you need to do is connect a load. You connect a load across it like this. So for example, you connect a light bulb. What you see is that the light bulb will enlighten. Is that okay? It will become bright. So once the light bulb lights up, then that is what proves that this has occurred. Then are we now done? No, we're not done. In fact, we're just beginning. Now, how does this occur? How does this really occur? Electrochemistry is what we study at the interface of here and here. That's majorly what we study. The interface between this and this. Now, what happens? How does electron get to begin to move? Now, this is what happens. Now, the moment we connected this, what happened is this, that you remember that we said there's a tussle for electron here, and there's also one for electron here, right? But why do electrons now eventually start to move here? The reason is because there is a stronger pull on electron on one side to the other. Now, how do I know that electrons will move from here to this place and not the other way? Now, that's where this thing now comes in. That's where this guy comes in, what we call the electrochemical series, EC series. Now, the electrochemical series comprised of both metal and non-metals. So we have the K CA, you must master this, okay? I'll give you a mnemonic, but I'll not finish it because I don't remember it to the end. FE, SN, PB, H, CU, HG, then there's platinum, there's AG, and there's AU. Okay? So from here, as it is, so we have this plus, plus, 2 plus. The charges are not exactly essential, but it helps you if you know them too. 10, I think is 2 plus as well. 2 plus, plus, 2 plus, 2 plus, platinum. Can't remember now. I think it's 2 plus. AG plus, AU, 2 plus. Now, I mean, of course, for the electronegative guys, you have OH minus. I usually start from F, then to SO4, 2 minus, NO3. No. Before this, we have Cl minus, Br minus, I minus, then NO3 minus, OH minus, CO3 minus, like this. I think this is it. Okay? Alright, but this is the part I want to focus on first, okay? Now the mnemonic I said I'll give it, I don't know the end is King Nathaniel can marry all Zion family. King Nathaniel can marry all Zion family. Then finish this one. I can't remember it. I don't know what. So now, why did I give you this? This series shows, it's called the electropositivity series too. It shows us which metals are stronger than which one when it comes to electropositivity. Which ones are more electropositive than each other. That is, which one can give electron and which one can withdraw electron. Which one has a stronger pull on electron or which one has a stronger push on electron. So now, it turns out that the higher you are in this series, the higher the metals are, the stronger the push they have on electron. The stronger the push they have on electron. So for example, these guys that are higher up here can push electron more, and these guys that are lower down here pulls electron. And it kind of negates what metals do normally, because metals don't accept electron. But because if I have, for example, in this case where I'm engaging copper and zinc, what will happen is that zinc will show its superiority by pushing up, dumping electrons to copper. Do you understand? So because this guy is higher in the series, this guy is lower in the series, this guy can push electron down to copper and copper will accept it. Is that okay? Or think of it as a tug of war where copper can draw electrons more than zinc can. Because zinc naturally doesn't want to accept electron, copper naturally doesn't want to accept electron, but if you put them together, connect them, one will dump electron on the other. Think of it as strength. Is that okay? For example, if I and Superman were to pull rope, who do you expect to win? Me, of course. I'm going to pull the rope and Superman will not be able to. Do you understand now? So that's the way it is. Copper pulls electron more than zinc does. So that's why I'm able to tell that zinc is going to be the one to dump electrons now. Now, why did I draw this? Is because you could be given a chemical reaction like this now. So for example, I give a chemical reaction. I could just give you a chemical reaction like Mg2 plus maybe lead to give Mg plus C plus lead Mg2 plus. Now you are now asked where did the electron go here? Now all you need to do is just check Mg2 plus to Mg. What happened? Electron has been what? Has been gained. So this one, electron was gained here. Well, actually, this is not what will happen. In the real case, what will happen is that, sorry, I made a mistake. What will happen is that this guy will be the one to dump electron on this guy. So this is the correct equation. The first one is wrong. This is the correct equation because this guy is the one that will dump electron on this guy. Why? Because it's higher up in the series. So it has, from here to here is what? Giving electron, losing electron. So that's oxidation. Is that clear? So that's what this series is for. So that you can know which one gives electron to which one accepts electron. Alright, so having said that, how does that exchange happen? Now this is what happens. On this surface here, this zinc metal is pregnant with electrons. Maybe think of it that way. Remember I said the guy that is giving electron, that is losing electron, that site is oxidation, right? So this guy here, this plate here, will be called the anode. Okay, so the reaction I want to write now is the anodic half reaction. Anodic half reaction. While the reaction right here will be the cathodic half reaction. So that's why we needed to do the redox reaction then. Now, since at the anode, what we said takes place. Now remember, at the anode, oxidation takes place. At the cathode, reduction takes place. So these are, remember, an ox, red cat, an ox, red cat. Okay? So, if oxidation takes place here, what happens? What is oxidation? Loss of electron. It means loss of electron takes place here, right? Who will lose electron here? Remember, when you have a positive charge on something, it means that thing has lost electron, right? Think of it as is hungry for electron. Why this one is pregnant with electrons? Has plenty electrons, right? Has too much electron. That's more of negative charge here. This one has lost some electron. That's more positive charge here. Has lost some electron. So where will electron go from here? This one that has positive charge here already losing electron. They lack electron. So electron will go from this guy, this zinc plate that is pregnant with electron, has not lost any electron. It will lose the electron. So how does it lose? One of these zinc here that I'm cutting out here, this zinc here, will leave this place. And it's not a mistake that I'm claiming it. It will leave this place and come and lose its electron and become zinc 2+. So what will it do? Zinc, normal zinc will lose. Zinc, when you lose something, that's minus, right? So it will lose its electron and to become zinc 2+. Is that clear? But then you say, Master, I've never seen minus in chemistry before. Yes. So this is what I want to do. We'll now use maths. We'll now carry this guy to that side, right? It becomes positive. So zinc becomes zinc 2+ plus 2e minus. You see, it proves to you. When I told you that when you find the electron on the right side, that's what? Oxidation. So electron is on this side, that's oxidation. A loss of electron. So this is the anodic half reaction. How about here, the cathodic half reaction? How does it occur? At the cathode. So it means that these two electrons, these are to do it, to migrate, to now go here. The two electrons will move here, move out, 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 and enter into this place. But of course, these guys, this copper metal, they are not the ones taking electron, right? Because they are stable. They are in the ground state. They are stable. They are neutral. So it's these guys here that need the electron. So this electron will come here until it gets to this interface and come and attach itself to this guy. Attach itself to this guy. Once it attaches itself to this guy will join this metal plate. So we have Ca2+ here. This guy will join this metal plate as normal copper. How does it happen? The Cu2+ before that was here has gained the electron that came inside and became Cu, normal Cu solid. Now these phases that I'm writing here are not important. So in case you don't put the phase, nobody will challenge you. So Cu2+ plus 2e minus, this is the balanced cathodic reaction. I told you. And what happens at the cathode? We say red cat, reduction, right? So, and I told you reduction. When you see electron on the left side, this is now reduction. This is how the reduction occurs. So am I not telling you that it just happen once? No, it will continue, right? Because the electricity will keep being generated. So since the electrons are moving, it means that this one again, zinc 2+, right? This one again, so maybe one here again, will lose its electron. It will lose its electron, become zinc 2+. This one again here will lose its electron, become zinc 2+. So those are 2, right? So 2 electrons have left now. 2 double electrons now. That's 4 electrons. They have left. So they'll come and this one will take up the first one. This one again will take up the second one. This one again will take up another one that will be lost by, so we have copper. That will be lost by, let's say this one again will lose its electron and join the solution as zinc 2+. Is that okay? Now, let me put one more. So we have lost 6 electrons now. 8 electrons. The 8 electron will come from here again. Keep in mind that the guys I'm choosing to lose electron, they must be inside the solution. No guy here can lose electron. So it is the guys that are inside the solution. So we have lost 8. Let's lose 10 electrons now. So our distance has become this shape. Are you seeing it? So another zinc 2+ has lost electron. So 10 electrons have been lost. So those 10 electrons will be taken up by this guy, which will join this guy. Let's say there was another copper here, will join this guy, but there's SO42- here, SO42- here. This guy will join solution, another this guy here. So let's shift this guy to this side. We'll move here, we'll join the metal, another Cu here. Let's shift this one here, SO4 2 minus, Cu2 plus. We'll join the metal here again. Do you understand now? So those 5 copper will join. I'm using 5. They are not 5. They are more. Okay. I'm just using the. Let's say it was quantizing. We could quantize it. I mean, of course, at the end of the day, the voltage can be quantized. Is quantized. But I'm just trying to give you the context. Okay. I'm trying to zoom in and so that you see for 10 copper ions gaining 10 electrons. So this is the same process by which all those 10 guys will form. Now, what do you notice over time? Over time, this guy will thin out to become slim, right? While this guy will become fat, and that's the truth. So, for most galvanic voltaic cells, what will happen is that this guy will become fatter. The cathode always gains mass. The cathode usually gains mass. Is that okay? Why this one usually does what? Loses mass. It loses mass. Do you understand? That is one thing you will notice that's one thing you will notice what voltaic galvanic cell. But there's a problem with this cell. Now this cell does not run continuously like that. Why? You also notice that as zinc is being lost here, is coming into solution as zinc 2 plus, zinc 2 plus, zinc 2 plus. So plenty pluses are accumulating here. Plenty. So pluses have accumulated here, and this place is becoming overall positive. And positives are leaving here. This place is becoming overall negative. So because of that, there is now separation of charge. So because of that separation of charge, this system does not run for long. So the solution to that is to immerse what is called a salt bridge. So immerse what is called what? A salt bridge. Bring in a salt bridge. This is called what? A salt bridge. Now, what is a salt bridge? A salt bridge is just an upside down U-tube that you place a salt inside too. Now you use a cotton here to stop the salt in its molten or solution form from entering into this place. So now what is that salt we want to use? So for example, we could use AgNO3. Silver nitrate. If we use silver nitrate, what will silver nitrate contain inside here? To be Ag2 plus or plus. Ag plus equal to is 1. Ag plus and NO3 minus. Ag plus NO3 minus. That's what you have inside here, primarily. Ag plus and NO3 minus. Plenty Ag pluses and plenty NO3 minuses. That's what you have here. Now, what do they do? What does that salt bridge do? The salt bridge helps to maintain neutrality. The salt bridge helps to maintain neutrality on both sides, in both cells. So why does it have to maintain electrical neutrality? Okay, electrical neutrality. Why does it need to maintain electrical neutrality? Because what will happen is that there will be separation of charge. So when that separation of that charge happens, this thing can no longer run effectively again. So for effective running, the salt bridge will help to neutralize it. So as positive charge is aggregating here, what will be moving here? NO3 minus. Minus will be flowing here. It will be attracted to this place and be flowing, so that it will be neutralizing the positive charge that is building up here, and the Ag pluses will be entering here to be neutralizing the negative charges that are building up here. Do you understand now? So that is what happens in a voltaic or galvanic cell. Now, listen carefully. There is a last part that you need to understand now. This part is the part that has to do with the calculation. Now, this is what we now have to calculate. Now, what is the voltage of this cell? The voltage of the cell. We call it cell potential, okay, for each of the cells, right? Now, that voltage of the entire system, the entire voltaic cell, will be called now this cell potential, another name for it is also reduction potential. Reduction potential. Okay? Or we call it total or standard reduction potential under standard condition like this. The total reduction potential will be called E cell. Now listen. You must understand this term reduction potential well. Let me quickly explain you before I now explain something that will help you to understand this formula I want to give you. Reduction potential, what is reduction? The ability to gain electron. But this overall reaction contains both reduction and oxidation. So why do we define this in terms of just reduction potential? Yes, that's the way we treat it. Remember that this one is not being reduced, this one is being oxidized, while here is where reduction is taking place. How do we now define the entire thing as reduction potential? Yes, it makes sense, of course. Now take note that the E cell, or the reduction potential of the cells, is equal to the reduction that happens E cell at anode. Remember, I told you cell potential is also reduction potential. E cell at cathode plus the reduction potential at anode. The E cell, that is reduction potential, is equal to, of the entire cell, is the reduction potential at the cathode plus the reduction potential at the anode. Now, but we know that reduction does not happen at the anode. What happens at the anode? Oxidation and ox. So E cell is going to be the reduction E red at cat, right? Plus E red at an. But you know that reduction does not happen at anode, right? So how do we transform this? Remember that E cell at anode is equal to E ox, right? Because it's oxidation that is happening at anode. But we don't define E cell as E ox, right? So E ox will be negative E red. Because oxidation is the opposite of reduction, right? So it will be negative of E reduction that is happening at anode. Is that clear? So what that happens is that our E cell, the formula therefore transposes to E reduction or E cathode minus E anode. Why? Because it is the opposite of reduction that happens at anode, which is oxidation. Now, for this cell, how do we calculate it? What's the E cell at cathode? Remember, this guy is our cathode, right? This plate here is our cathode. Now, how do we now calculate E cathode? How do we calculate E anode? There's a standard E cell. Now, there is E standard minus E standard of anode and cathode. But how do we get the E standard now? That's what I want to teach you now. Now, there's something called the standard. Let me bring it here. We call it She, okay? Standard hydrogen electrode. Now, let me show you what that is. Now, to calculate the E cell of the standard E cell of a particular metal, of a particular electrode, we use a cell that contains hydrogen. So now we call it the standard hydrogen potential. Standard hydrogen electrode. We use the standard hydrogen electrode. So what we'll do is that we'll compare, instead of use, for example, if I want to operate if I want to check for the cell potential of zinc metal, there is a table in your textbook that will contain all these numbers. But I want to teach you how it was gotten. Is that okay? So if I want to get the cell potential of zinc, I'll compare it with a standard hydrogen electrode. Okay? The standard hydrogen electrode is the one that uses hydrogen, okay, hydrogen gas. But this is the case. The standard hydrogen electrode is designated E cell of 0 volts. The She is designated E cell of what? Of 0.00 volts. Is that okay? Given to 2dP in this case. 0.00 volts. Now what that means is that when you compare any other one with it, the value will now be the recorded value. So how it is done is that there is a U-shaped tube through which the hydrogen will be passed inside, and then there is an electrode that is immersed inside a solution of an acidic solution, okay? So inside this acidic solution, you have H plus, if it's H2SO4 or HCl, here's HCl, you have H plus Cl minus, H plus Cl minus, okay, H plus Cl minus inside. Now, there's something with this electrode you have to remember, that you need to remember. You see these electrodes here, the electrodes here, in this case, the electrodes are used up, the electrodes are affected. Okay? The electrodes are affected. But here, the electrode that is used here is an inert electrode. This guy uses what? An inert electrode. That is an electrode that is not affected, inert electrode. This guy is an inert electrode. Inert electrode that is not affected during the process in a cell. Is not affected by the electron. The electron doesn't gain electron or lose electron. An example of an inert electrode is platinum. Platinum is an inert electrode. Another example is platinum. I can't remember. Now, some electrodes that are not inert, they are reactive electrodes. Affected, it means because they are reactive. Okay. Example of reactive electrodes are nickel, copper, they are reactive zinc, those ones that we just used, okay, they are reactive electrodes. But inert electrodes, we have platinum, I think manganese also is this thing. But the one we use for hydrogen, the hydrogen electrode is what the platinum, because it doesn't get affected. Now what happens is that hydrogen is passed into this place. Okay, hydrogen is passed into this place is passed in here. Hydrogen is passed in here at standard temperature and pressure. Okay, standard temperature and pressure. What is standard temperature? That will be 25. I'm sorry, not standard temperature and pressure. Sorry, at room temperature. At room temperature. Now, what's room temperature? That is 25 degrees Celsius. But we use Kelvin to record. That will be 273. That will be 298. Yes, 298 Kelvin. So, and pressure of 1 atm. 1 atm, okay? Now, you might see your textbook designate 1000 kilopascal. It's because 1 atm is actually equal to 1.0 times 10 to the power 5 Pascal. So if you do that, put 100 here, that becomes 1000. The rest becomes 1000, that's 100,000 pascals. Exactly. So at this temperature and this pressure, you set in this guy into a solution of HCl. That HCl solution, the concentration is 1 mole per dm³, okay? Or 1 molar solution. Now, when you set it in, this is the cell potential for, you can get the cell potential for a hydrogen electrode like this is designated as, I have told you, this volt. Now, when you now want to do is, you now connect this to another system here. You now connect it to another system here. So I'm going to draw. So if you want to calculate for zinc now, you now take this zinc plate, you now bring it in. Let's do for copper first. If you calculate for copper now, listen, there's a reason why I'm starting with copper, there's a reason. If I want to calculate for copper, then I'll connect a wire, right? I'll connect a wire. That wire will be connected to this electrode. So maybe it's going to go through this tube. But let me just put it through here. Now when it goes through this place, you connect this, your copper, this, your copper, this, your copper. Now what will happen here? Tell me what will happen. Now at this point here, the pressure is 1 atm, like we said. Now, what will happen here? You must connect a voltmeter here. You connect a voltmeter here. Keep in mind also that your electrolytic cell that we're going to be discussing is also a voltmeter. Let me check the level of this thing. 10 gig. Okay. Now, so you connect a voltmeter here. Now, when you connect a voltmeter here, the voltmeter is not going to be recording the voltage of this thing. But now, this thing, this guy that is connected this way, there is a reason why it's connected this way. This guy becomes your anode, right? This guy becomes your anode, and this guy becomes your cathode. But what happens? Who will give electrons? Who will accept electrons? Now, look at it here. Hydrogen is higher in the series. Copper is lower in the series, isn't it? Since copper is lower in the series, then hydrogen will be the one to give this guy electrons. So when this guy gives that guy electrons, the anodic half reaction becomes becomes H. So H plus would hydrogen is here, right? They will donate electrons. So hydrogen gases will donate electron to this guy. They will donate electrons, so they will lose electrons. So that will be minus 2e minus to give H plus ions. H plus ions. So how do we write this? Bring this guy over here. Just remember this method I'm using. We'll give this gas, we'll give electrons out, so they will lose electron in this reaction. Is that okay? So when this happens, at this point, these guys will be taking electrons, Cu2 pluses that are inside the solution, Cu2 plus, Cu2 plus, Cu2 plus. You can use SO42 minus as well. That is copper sulfate. Okay, so this guy will gain electron. So when he gains the 2 electrons, then he forms copper solid. Okay, but the idea is this. Notice that these electrodes will also be affected, right? But the point is that this voltmeter will be able to record the cell potential of this point. What is that voltmeter measuring? The voltmeter is measuring how much strength this guy is having to draw electrons from this guy. So think of it as measuring the charge the value of the energy that is using to draw the distance. So by standard, actually, copper is able to draw this thing, electron, at what is called plus 0.34 volts. Now take note of this positive. Take note of this positive. Plus 0.34 volts. Now, here's the case. With this thing, the case is quite different. With zinc, when you connect your two, this zinc, and zinc 2 plus. The same system. And of course, SO4 2 minus. Now here, you're going to have your electrode, your inert electrode that is not affected, then your U-tube. So this guy is connected like this. Okay? So don't rely on my diagram, okay? It's just somehow. So this inside this tube, what do we have? We have hydrogen, and we have H plus. Now, what is happening is that in this case, what will happen? Then you connect what here? You connect your voltmeter to record the voltage, right? In this case, what will happen? A different thing will happen. Yes, a different thing will happen. What's that different thing that will happen here? Now, given that the zinc is higher up in the series here, the zinc is higher up in the series, what will happen? It will be the one to donate electrons. So remember, the direction of the electron here, in this case, the direction of the electron is like this, right? 2 electrons are moving like this, in this direction. Electrons are moving in this direction, right? They are moving in this direction. But in this case, electrons will be moving in this direction. Electrons will move in this direction. Electrons will move in this direction. Two electrons like that too. So that the cathodic half reaction will look like this. Now in this case, this will become the anode, this will become the cathode. Is that okay? Because this is where position. So this one will now be anode. And this will now become what? The cathode. But keep in mind that, so it means that we have to reverse the way this thing happens, right? We have to redraw it. Okay? So zinc will lose electrons, so that becomes zinc. Just follow what we wrote the other time. Zinc 2 plus 2e minus. Then this guy will now gain electron. H2 pluses. 2H plus will gain electron to become hydrogen gas. So hydrogen gas is formed here. Is that clear? So this is the anodic cathodic half reaction. So it's anodic half reaction. Now keep in mind, listen, this is what you have to now keep in mind. That as electrons are moving here, this voltmeter will now record a reverse direction. Do you understand? Sorry. So listen. You won't change this direction. You won't change it, because that's the reason why we always arrange the hydrogen electrode first, so that when this voltmeter wants to record, it records this direction, so that since the electrons are now moving in opposite directions, it will now be negative. So what is recorded for this is actually 0.74, that is 76 or something. I can't really remember volts, but I think it's this. Do you understand now? So it alternates it. The value of this is actually 0.74 0.337. I think I remember now. And this one is 0.763. Okay, yes, so I'm correct. So the reason why it's negative is because this, you don't change this position. The standard hydrogen electrode must come first. The standard hydrogen half cell, that's another name. Standard hydrogen half cell must come first before the other cell. If you want to record the cell potential of that cell. So the reason why some values on that table are negative is because they are the ones donating electrons to what? To hydrogen. They are the ones being oxidized. Exactly. So since they are the ones being oxidized, the electrons are what? Moving in this direction for that reason, and then the voltmeter is recording negative value. Is that clear? So it means I wanted to calculate for this guy that we just did here, then the E cell for our reaction, E cell becomes E cathode. What's our cathode now? Our cathode in that case is this, that's copper. It's recorded plus 0.34 volts minus our E anode. What's the cell potential for zinc? Is minus 0. That will be minus 0.76. So this becomes 0.34 plus 0.76, which gives you 1.1 volts. So for a galvanic cell, this galvanic cell, the cell potential eventually is what? 1.1 volts. So that 1.1 volts is the voltage of this, if this were to be operating as a battery. So if you connected something here, the thing will be enjoying 1.1 voltage of electricity. Do you understand now? So that is how we find standard hydrogen potential. That's why it works. And electrode potential. Now, so that's majority of the calculation that you need to know here. Then of course there is also the Nernst equation. Let me just write that for you. But what I will do, if you want me to derive Nernst equation for you, okay, that's it. There's the Nernst equation that I also like to derive. If you want me to derive the Nernst equation for you and explain what it means. See, you see why students feel these things, that they don't understand what Nernst equation means actually. They don't understand it. So I will derive it for you and explain what it literally means. And I promise you that you'll understand. Okay, so if you want me to derive it, put it in the comment section that I should derive it. I want to be sure that you saw this video till the end. If I just dump everything here and I'm not getting responses, it won't be encouraging. So let me know. I'm going to derive it in a separate video, short separate video. And then let's go to electrolytic cell actually. Electrolytic cell. Now, let us begin electrolytic cell. Now, you see, electrolytic cell uses electrolysis, okay, the process of electrolysis to operate, okay. Now, what does electrolysis mean? It's got from two words, electro, meaning electricity, and lysis, meaning splitting, right? To split, it breaks apart, right? So, if, for example, Voltaic cell is the principle of operation within your battery, then inside your battery, then the process that reverses it when you use up your battery. When you use up your battery, that's Voltaic cell. When you now recharge your battery, that is electrolytic cell. Is that okay? So electrolysis is the process that recharges your battery for a secondary cell. But of course, I didn't even mention that before. There are two types of cells. We have the primary cell and the secondary cell. Primary cells are not rechargeable. Secondary cells are rechargeable. So my point is now that the process that recharges your battery is electrolysis, okay? But the concept of electrolysis that we'll be discussing here is not even that process of recharging the battery. It's actually how we use electricity to split things. So for example, we are going to be talking about electrolysis of brine. Electrolysis of brine. Now there are two types of brine. We have dilute and concentrated. But this guy we are dealing with is going to be a concentrated brine. So what is brine solution? Solution containing salt, NaCl, and water. So what we want to do primarily is achieve this thing. Achieve Na solid breaking down, NaCl breaking down into Na. Now Na is not going to be solid, in that case maybe liquid, and Cl2 gas. We want to separate these guys. To balance, we put 2 here and put 2 here. So what we want to achieve is basically do this. Now, in a normal laboratory process, we cannot really do this. Okay, so what we want to do is use electrical energy inside our battery to force it to happen. So, that in mind, you already know that we need a battery. We need a battery at the start, right? Now, we could draw a battery, but I'd just like to use the cell notation for battery. So, it's going to be something like this. Let us put it, we like to put anode first, right? And this side, so positive, so it should be like this. Eden is no more a place. I am the city of God. So this is positive, this is negative. So it will be connected to a metal plate. Okay? In my school, with my students, I used and that was not this year student, I think that was last year. We used a spoon and a nail. Okay? But we like to use inert electrode, okay? Iron is also an inert electrode, iron. So platinum, iron, I am just remembering now. Is also this thing, inert electrode. And I think carbon, I can't remember. All right, so, oh, sorry. Then it's not two cells, it is one. This one. Of course, remember in that guy, I didn't put YouTube, I didn't put a salt bridge. In that standard hydrogen electrode, you also put a salt bridge. Okay, so this is the case where inside one system, this is our electrolytic cell, but it's not yet complete. We have to put something here, right? Put water here. After putting water, put a lot of, not a lot of salt, but put salt so that it is concentrated. It is filled with salt. That's not concentrated, it is full with salt. So there's many Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus. And of course, because there's also water, there is water dissociating. You know, so what we have here is NaCl dissociated to Na plus and Cl minus. Then H2O has dissociated to H plus and OH minus. So if this is the case, then it means that we also have H pluses, OH minuses, OH minuses, H pluses, OH minuses, H pluses, and OH minuses. We have them everywhere. Okay, so they also fill this place, right? So these are electrode. This one that is connected to the positive part of the battery. Remember, a battery and a cell, they are pretty much alike. A battery is an aggregation of cells. So a battery could be one cell or many cells. So this is many cells, like 3 cells here. Now, the electrode that is connected to the positive arm of the battery is the anode. So that's how we call it the anodic and the positive electrode. So this is the positive electrode. It is the positive electrode. While the cathode is the negative electrode. Is that okay? It's the negative electrode. So this guy is going to be our anode. This guy is going to be our cathode. Remember here, no YouTube, no salt bridge. All right. So now what happens the moment you connect this to a battery? Now here's what happens. The battery will be supplying electrical energy here, so that electrical energy will be converted to chemical energy of separation here. Is that okay? Chemical energy of what? Separating this thing. Is that clear? So now for those of you that are doing written tests and exams, that's why I'm doing this with detail. Listen, you are going to write, now something will happen. There's going to be discharge of electron. There's going to be what? Discharge of electron. Discharge of ions. Sorry, did I say electron? I'm sorry. There's going to be discharge of ions. Now there are some factors or conditions that determine which electrons will be discharged. What does discharge mean? It means some ions will be told to leave the solution. They'll be kicked away out of solution. That's what it literally means. So what are the conditions that determine who will be kicked away? The first one, there are about maybe 4, I can't remember. But I know that the position of the ion in the EC series, the position of the ion in electrochemical series, it determines it. So now what does this do? The higher up you are in the series, the less likely you are to be discharged. So the guys that are up here, they are the ones that are likely to discharge the guys that are lower here for metals. Is that okay? Then for non-metal, the guy that is lower here, this is the most electronegative, is likely to discharge the rest that are above here. So while this one above here is the electropositivity series, this one will be the electronegativity series. Is that okay? So, and as you go down like this, the electronegativity increases. So this is the most electronegative ion, then the rest follow like that. So this one too is the most electropositive ion, then these ones follow. All right. So the point is this: in a solution where you have calcium and potassium, of course, which you don't want to engage in your laboratory because it will be very vigorous. But let's say to a positive, hypothetical, in a hypothetical condition, this guy will displace this guy, will discharge this guy. You connect calcium itself and aluminum. Calcium will kick away aluminum out of solution using this opposition. If you put aluminum and tin, aluminum will kick it to slap tin on the face and tell you to get out of the solution. So tin will be discharged. You now put tin and copper, tin will slap copper on the face and tell copper to get out. Actually, you will hear it. You will hear the other guy telling the other guy to get out here. You will hear it. You will just hear from them, get out. It's these guys that are talking. They actually talk. That's a joke though. Now, mercury and silver. Mercury will tell silver, get out of this place. The lower you are in the series, the more likely you are to be discharged. Now, so that's opposition. Another thing that determines who will be discharged is the concentration. And this order is very important because position is the first most important thing. But the second important thing is the concentration of the solution, of the electrolyte. Now, if the concentration means how much abundant is this guy. So if NaCl is very abundant inside water, then it will affect who will be discharged. Do you understand? So the abundance of that electrolyte, of the solute in the solvent is very important. Then the next one is the nature of the electrode that is used, the kind of electrode used. Now, if you use an electrode that participates in the chemical reaction, then it may affect what will be discharged. Okay? I'm going to give you an example. For this concentration here, for example, using position, now listen to me, using position, who should be discharged here? Between sodium, there are two metallic ions here. We have sodium metal and hydrogen ion. They are the ones that are in the positive side, right? They are the electropositive guys. Who should be discharged? According to position, it is sodium, it is hydrogen that should be discharged because hydrogen is lower. According to position. But actually, we see that for electricity of concentrated concentrated brine, we see that it is sodium that is being discharged. And there is a reason. The reason is because it is concentrated. So sodium is very abundant. So let me go and explain that now. And I'll also explain nature of electrode. I'll explain nature of electrode. Let me first explain with this our guy. Let me see if this thing is still recording. 7, wow. So now watch. This is how you write. You write at the anode. At the anode. What happens? Now what will happen to the anode? You know the anode is positive plate, right? The cathode is negative plate. So what will happen? Positive and negative attract. So the negative guys, they will be attracted towards it. So what you will find around this guy will be what? Cl minus, OH minus, Cl minus, OH minus, Cl minus, OH minus. Now what will you find around this guy? You will find H plus, Na plus, H plus, Na plus, H plus, Na plus, H plus, Na plus. They'll come and aggregate themselves around here. While this one, they'll come and aggregate themselves around here. So if that's the case, when that happens, so you say that at the anode, migration of whom? Migration of anions. Migration simply means movement of anions. So anions, who are the anions here? After ionization, these guys are the anions and these guys are the cations. These guys are the and these guys are the cations. So migration of the anions to the anode. So who are the anions? The Cl minus and OH minus. Both of them have migrated to the anode. So there is now something that will happen. One has to leave. Two of them cannot stay. Two chiefs cannot stay in the town. Or two kings cannot really stay. So one has to leave. So we are now to determine whether it is Cl minus or OH that should be released. Now, according to position, the first condition for releasing, for discharging, Cl minus is stronger because the lower you go, the stronger. Cl minus is stronger, so you should naturally tell OH to get out of the solution. But here's the deal, because the solution is concentrated. Now, this guy actually has the audacity to tell this one to go. Actually, he doesn't even use the audacity. This is the reason. This is what happens. They will not lie us. This one now say, see, we are not plenty now. This one now say, we are plenty. So thermodynamically speaking, it is actually, the result is actually thermodynamic, um, thermodynamic effective, thermodynamic favoring. Yes, sir. Thermodynamically favored. Yes, sir. So the result is actually thermodynamically favorable than talk of this. Thermodynamically speaking, it uses less energy. There is less energy for discharge of an abundant guy. Something that is abundant is easy to kick it off. Do you understand? It requires not much energy to kick off this Cl because it's already plenty. It's too much. Do you understand? So because of that, Cl minus will be discharged. How does it get discharged? Now, how does it get discharged? It will, now, this guy that is negative, will he lose electron or gain electron? It's the positive guy that gain electron. So this guy what? Loses electron. So this first guy will lose 1 electron and become Cl. Okay? But we don't use negative, right? So you say I like to use lose. I like to, so that you understand that it's simple. And you understand that then you now convert. Because some students, I've seen my students complain that electrons, that how do you show electrons as lost when it is here? They say, where would the electron stay? Here's how to start it. Electron is lost. So you now bring it to this side, Cl minus to Cl plus E minus. But actually, this guy does not form like this, okay? What will happen is that another Cl minus will undergo the same process so that the overall reaction will become 2 Cl minuses will lose 2 electrons to now become Cl2 gas because this guy is divalent. So because of that, when gas is formed, for example, if it's oxygen to be O2, Cl minus, chlorine gas is Cl2, N2, F2, Br2, all those guys like that, these are how they form. So to form a gas like that, it has to be like this. So this guy will now go there and become Cl minus to give Cl2 plus 2E minus. So this is how Cl2 gas is formed. Is this clear? So then this Cl2 gas will now leave the solution. That's why you now see your solution turn greenish yellow. The solution will turn greenish yellow because this guy is leaving. So, chlorine is leaving and people are crying. All right, then how about at the cathode? Then at the cathode, what happens at the cathode? Now at the cathode, who and who will migrate to the cathode? Cations migrate to the cathode, cations to the cathode, anions to the anode, cations to the cathode. Okay, so at the cations migrate. Cations migrate. Now, when cations get there, what will they do? What are the cations? Na plus and who? H plus. Now, naturally, sodium is not his mate. Sea level. You to sea level now. Sea level. Sodium should naturally, when sodium, actually, this is the way it happens. When sodium steps into the cathode ground like this, just get there. All the hydrogen will start hiding. I've seen it happen before. Because you even look at it here now. Okay, man, they are not hiding, right? But that's what they normally hide in real life. They normally hide because sodium, when they see sodium is big boss. See sodium. See the people he's rolling with Mr. President. Do you understand? He's rolling with, so you cannot, so sodium is not his mate. See how far they are. So this guy should naturally go. But sodium will now say, because of energy sake, thermodynamically speaking now, it is easier to release sodium that is plenty than hydrogen. So the process of releasing sodium is thermodynamically favored than hydrogen. So that's the only reason, concentration sake. So that's why you should keep in mind that it is concentrated. Meaning that in a dilute case, reverse would be the case. So in this case, we'll discharge OH minus. So meaning that oxygen will be formed. Now this is it. If you want me to release a video on electrolysis of acidified water, I'm going to do it. It's very simple. What will happen is that oxygen will be ejected from here. Oxygen will be, produced from here. So that will give you O2 and more like, we have in water, we have H plus and OH minus. So we want to discharge oxygen. So this guy is going to form oxygen, O2. So H2O is forming oxygen and 4H process. Okay? Because if it's two water, so that will be two oxygen. So 4H process. Okay, so this will be the reaction for the distance being lost, then plus 4 electron for oxygen being produced. This will be the case if it were in a dilute reaction where IOH is being discharged. Is that clear? But in this case here, it's not the case. Position does not take priority. Concentration is what takes priority. I will end with this nature of electrode before we do calculation. But if you want me to do electrolysis of acidified water, because the conditions are even different with that, we don't use this system. I'll show you if you want me to. So put it in the comment section, I'll respond. Now, Na plus and CH plus, so what will be discharged? Sodium. How will sodium be discharged? Na plus will gain, because it's positive, to gain electron, the electron that this guy lost. But this guy lost 2 electrons, right? So it has to gain 2 electrons. So Na will gain electron and become Na solid. Another Na guy will also gain another electron and become Na solid. So they will now aggregate. Na plus Na will now form 2Na. Not Na2, it is 2Na. This guy is not divalent, so that's why. That's why it's like this. So this guy is solid, is now formed. Is that clear? And that's the product of electrolysis of acid of brine. If it were dilute, of course, hydrogen will form hydrogen gas. Hydrogen H plus will be discharged, and hydrogen will aggregate to form hydrogen gas. I will do that in acidified water. Now, what about nature of electrode use? How does it affect? So, for example, if you are doing a solution, an electrolysis using copper sulfate, and you now use copper electrode, copper will be discharged because copper electrode will cause copper to be discharged. Because copper electrode is affected, is not inert, it is a reactive electrode. Is that clear? So that is what happens. That's how nature of electrode affects it. But in this case, we are using an inert electrode, doesn't affect our reaction. So because of that, these two take priority. Is it clear? Now let's go to calculation with electrolysis. We'll start with the laws of electrolysis. Alright, so in order to wrap up the video quickly, I'll just discuss laws of electrolysis and I'll solve these 5 questions and we'll wrap up the videos. Now if you need me to send you questions, reach me out on that WhatsApp number. I'm going to send you questions, or you need an aspect, those aspects I ask you to make video, ask you to, if you want me to make videos on, put it in the comment section, okay? Now, laws of electrolysis. There are 2 laws of electrolysis propounded by Faraday in 18, I forgot it. So Faraday propounded the first law, where he said that the first law of electricity states that the mass of an element discharged, the mass of an element, you can write that down, the mass of an element discharged in an electrolytic process is directly proportional to the quantity of electricity passed through it. Mass discharged is directly proportional, mass of an element discharged is directly proportional to the quantity Q of an electricity, the quantity Q of electricity passed through the solution of the electrolyte. Is that okay? Quantity of electricity passed through the solution of the electrolyte. Alright? Alright, so that's provided that the electrochemical equivalent is kept constant. So now, mathematically, we will say that we interpret that as mass is directly proportional to the quantity of electricity. And recall that quantity of electricity is IT. How did we get that? Current is the rate of flow of charge, right? So Q will become what? IT. So if that be the case, this equation becomes, this is direct proportional to what? IT. So by the time we introduce our constant of proportionality, which is Z, it becomes M equal to ZIT, where Z is the electrochemical equivalent. Mommy, Ma, Okay, so now we said that is proportional to the electrochemical equivalent. And what is this electrochemical equivalent? EC for short. Now, electrochemical equivalent is different from chemical equivalent. Chemical equivalent. This is different. Now, electrochemical equivalent is the amount of electricity. Electrochemical equivalent is the measure of. How do I define this now? Electrochemical equivalent is the mass of element discharged when a current of 1 ampere is passed for 1 second. Is that okay? That is that is the electrochemical equivalent of that metal. Is that okay? So that is that. Now, using formula approach, okay? Using formula approach, the electrochemical equivalent, I told you, is going to be this Z is actually standing for the mass discharge, as I said, the mass discharge, that will be RAM of the metal that will be discharged times the quantity of electricity passed through it over the quantity of electricity what's it called now? When 1 Faraday, when the times over number of moles of Faraday, that is number of moles of electrons that is used. Okay, this is the formula. But I'm not teaching you the formula method yet. I'll teach you how to use the formula directly though. So this is the first law. How do we apply the first law? Let's solve the first question. In fact, all these questions are based on the first law. So I will treat the second law later. Now watch. But I'll give you what it states first, the second law. So now watch. And excuse me, I'm trying to finish off quickly. So mass, I said, calculate the mass of the silver deposited when a current of that. So question 1, when a current of 2.6 amperes is passed through a solution of silver salt for 70 minutes. Time is 70 minutes. We have to convert this. Conversion goes to seconds, that's times 60, becomes 7 times 6, 4200 seconds. So, and silver is the one that is being deposited here. All right. Now, you should be able to write an equation, an expression for the deposition of silver. So, how do we write the equation? That is the cathodic half reaction becomes Ag plus 1 electron. Okay? Before we write this, let's calculate the quantity of electricity that is passed. The quantity of electricity will be I times T, right? That will be 2.6 times 4200. Let's use calculator for that. So this becomes 4200 times 2.6. Becomes 109, 10,920. So this is the amount of electricity that is passed through it. So now, if silver, how is silver being discharged? This is the way it is being discharged at the cathode. So the cathodic reaction now. The cathodic reaction will look like this. Ag plus is being discharged because Ag, that's why you must know the charge, okay? You must know the charge. Ag plus E minus. So will give us, if you gain electron, it become Ag solid. Is that okay? So this is how it's being discharged. So this equation, why is this equation necessary? It helps us to know how many Faraday is being discharged. Actually, there's a trick to knowing that. But how many Faraday is this? 1 electron is equal to 1 Faraday. So 1 Faraday is how much quantity of electricity? 96,500. So what this equation is saying is that Coulomb. What this equation is saying is that this 1 Faraday, which is 96,500 Coulomb, is the amount of quantity of electricity that will discharge this is 1 mole of Ag, right? Which is 108 in grams. So 108 grams will be discharged by this normally. That is on a normal condition. This is the ideal case. In the ideal case, 96,500 coulomb of electricity discharges 1 mole, which weighs 108 grams for silver. Therefore, we now passed this. This was the amount we passed. We passed 10,920 coulomb into it. What is the mass that it was discharged? That's how to solve it. You cross multiply. So when you cross multiply, you're going to have that x times this becomes 10920 times 108. Divide both sides by this gives 96,500 here. And if you look at it, it already follows what we did here. The formula mass will be equal to the RAM times quantity of electricity divided by number of Faraday. 1 Faraday, that will be 1 times this. You see? So it becomes this times 108 10920 times 108 is equal to this divided by 96500 is equal to 12.22 grams. So I'm doing to 2 dp. So 12.22 grams, and that's the answer. How about number 2? So for number 2, I can use the formula directly because it works. But you have to know this method because this method is for written exams. This way you have to, spell out your things. Using copper electrode during the electrolysis of copper sulfate. So you see, it needed to be specified that copper electrode was used. Because if an inert electrode was used, maybe copper will not be discharged. So copper was discharged when the current of that I is 3 amperes. I'll manage my handwriting, okay, please, because I'm trying to squeeze in the space. 3 amperes flows for 1 hour 5 minutes. 1 hour 5 minutes. Maybe it's 1 hour 15 minutes. I even wrote 5 minutes there. But anyways, we can still calculate with it. 1 hour 5 minutes. How do we convert that? 1 hour to seconds will become 1 times 60 times 60. Then plus 5 minutes to seconds. 5 times 60. 300 plus 3,600. That becomes 3,900 seconds. So the quantity of electricity passed therefore become I times T, which is 3 times 3,900 equals 3 times 3,900. 11700 coulomb. This is the quantity of electricity that is passed. Okay? So if I wanted to use formula, I already know this. My formula N becomes RAM or Q times RAM over NF. So this becomes the formula. Q, I've known Q to be this, 117 or IT RAM, okay? Each RAM, or RAM it. RAM it over NF. That's another way to remember it, okay? Okay, once this times RAM. What is RAM now? The RAM of the metal, which metal is this? Copper, 63.25. 63.5 rather. Divided by NF. Now, what's the quantity of electricity that will be discharged when you ionize this thing? Copper. You want to discharge copper, it will be Cu2 plus gains 2 electrons, okay, to give Cu solid. So C equals. The phases do not matter, I've told you that before. So 2 Faraday is needed here. So 2 Faraday is needed here. 2 Faraday will become 2 times 1 Faraday, which is 96,500. So this is what you do. M equal to all of this times 63.5 is equal to this divided by, this will give us 193,000. So divided by 193,123 is equal to 3.85 grams. Let's see if it makes sense. If 11,700 coulomb is passed, if normally if you pass 2 times this, 2 times of this, that is 193,000. If you pass 193,000, it takes 193,000 to discharge 63.5 grams. So if you now pass 11,700, which is very, very less, you should get something this small. So that our answer makes sense. Is that okay? Then the next one, number 3. Number 3 says that how long will it take to deposit 4 grams? So we just make T subject to the formula, right? So if you make T subject to the formula here, it becomes T becomes mass times mass discharge now, mass deposited times quantity of NF divided by RAM of the metal times current. Exactly. So T therefore becomes, what's the mass deposited? To deposit 4 grams times NF. What's the metal? That's silver. Silver needs 1 Faraday, right? Silver needs 1 Faraday. So that is 96,500 times 1. Is that okay? Over RAM of silver is 108 times, what is I? Current is 2.5 amperes. You see I solved it now? Very simple. T equal to 4 times 96,500 is equal to that, divided by 108 is equal to, and divided again by 2.5 is equal to, so the time is 1 1429.63. Okay, so if you turn this to this in seconds, okay, you turn this to how to minutes divided by 60 now equal to 23.83 minutes. Okay, so this is the answer. All right, for number four says we should calculate the amount of gold deposited when a current of that, okay, so the mass equal to RAM. What's the RAM of gold? 197. First, let's write the parameters. We're looking for mass. The current is 5 amps. Through a solution of gold for time is 2 hours, 5 minutes, 15 minutes. That one is 5 minutes, right? Yes. So 2 hours, 15 minutes, that will be 2 times 60 times 60 to convert to seconds, then plus 15 minutes to convert to seconds times 60. This times this, 16 times 5, 90. Let me use calculator. 7,200 now, plus 90, plus 0, 900 now. So this becomes 8100. So coulomb. So we've gotten the amount of coulomb. So mass becomes RAM, which is 197, times IT, which I have calculated. No, this time here. Sorry, this time here. So that'll be 5 times 8100 divided by NF. So to deposit gold is AU2 plus 2E minus to give AU solid. So we need 2F, right? So that will be 2 times F, which is 96,500 coulomb. Exactly now. So that becomes 197 times 5 times 8100. Is it 100? Yes. 3,600, yes. So is equal to that divided by 96,500 is equal to, and divided again by 2 is equal to, so mass equal to 41.33. That's 34 grams. So let's see if it makes sense. Yes, it will make sense because 2 farad is needed for 197. So this quantity of electricity is less than that 2 farad. So that makes sense. Then the question further says that if the same current, that's 5 amp, is used, find the time taken to deposit 6 grams. Very easy. Just use time equal to mass deposited is 6 grams times NF, which is 2 times 96,500 over RAM, which is 197, times current, which is 5. So very simple. You just do 12 times 96,500 divided by 197 divided again by 5. So the answer is the time is equal to 1175.63. So a minute, so this is seconds. A minute divided by 60 is equal to 19. It's equal to 19.5, that's 19.6 minutes. 19.59. 19 minutes, 59 seconds. 19 minutes, 59 seconds. 19 minutes. $59. All right. So this is what will happen. This one very easily. Solve this one for me. Calculate the RAM. Just make RAM subject of the formula. Make RAM subject of the formula. So here I will state the second law, and that is where we'll wrap up the video. Now, what does the second law say? The second law of electrolysis, Faraday's second law, states that if the same quantity of electricity, is passed through solutions is passed through solution of different electrolytes connected in series. It's passed through electrolytic cells connected in series, E cells connected in series to each other, comma. The mass of elements discharged is directly proportional to the chemical equivalence. So that's what I was trying to point out there. Chemical equivalence of the solution, of the metal, sorry. Do you understand? Of the metals. Now listen, of the elements that is discharged. Now listen, the way you will see this law being said in your textbook might be that the number of moles of element discharge is inversely proportional to the electrons, to the quantity of electricity, to the quantity of electrons gained. Is that okay? Now, let me interpret this. The formula is just M1, the mass of 1 is directly proportional to the chemical equivalence. E is chemical equivalence. Chemical equivalence is the amount, chemical equivalence is given by the molar mass, the RAM, per mole. So that's why you see inverse proportionality here. Yes, and between the mole and the chemical equivalence. So that's what you see there. So the chemical equivalence, so M2 therefore will also be equal to what? E2 will be directly proportional to what? Directly proportional to E2. M3, if they are connected in series, directly proportional to what? E3. So depending on what you are given, so E1 therefore will also be what? E2 therefore rather also be what? RAM of 2. So RAM of 1, RAM of metal 2 over number of moles of metal 2. Is that okay? So to put this all together, we can say that the first formula will be M1 over M2. If we take the ratio, will be E1 over E2. Is that you use this equation 1, or you use this to solve where you are given chemical equivalence. If you are not given, you use M1 over M2 is equal to RAM1 over N1 over RAM2 over N2. This formula reverts to, this formula becomes M1 over M2 equal to RAM number of moles of 2 over, this will come down, RAM, this is RAM1, RAM2 times number of moles of 1. Is that clear? So it's very simple. Just know your first metal, know your second metal. Once you designate, you use the RAM of your first metal, divide by RAM of second metal, times number of moles of second metal, times divided by number of moles of first metal. So you see here, you don't need Faraday. You don't need quantity of electricity as well. Alright, so this will be it for this video. If you want me to now solve other questions on second law, do well subscribe to the channel and let me know in the comment section. Then drop your answer for this one in the comment section. Is that okay? Drop your answer in the comment section. God bless you as you subscribe to the channel and share the video with your friends.